Okay, this is the second PowerPoint of Unit 1, and this focuses on periodic trends and being able to explain periodic trends. So one common periodic trend that you've probably learned about in honors chem or pre-AP chemistry is atomic radius. Simply, we just call this the size of an atom or the distance between two bonded atoms, but technically it's 1/2 of the distance between two identical atoms covalently bonded to each other. So really just think of atomic size. Here is the trends, and it's good to know these as you go across a period. Notice the size is decreasing. As we go down a group, the size of atoms is increasing. So it's good to know those trends, but more importantly, on an AP question, just saying what the trend is will not get you any credit. You have to explain why are these trends what we observe. Okay, and we're going to get to the explanations later. So let's just go over the general trends first. So number 2 is the ionic radius. Okay, so we're talking about the size of... Okay, so ionic radius, notice two types of ions. Cations are positive and anions are negative. So let's focus on cations first. Remember, this is where electrons are removed. And notice, here's an example right here with lithium, that cations are smaller than their parent atoms. Okay, so we can notice this lithium ion is smaller than the lithium atom. So let's think, why would this be so? And notice in parentheses it says the ion has electrons in a lower energy level. So if we go back to our electron configuration, we see that lithium, we write it from one of our previous slides. Oops, got carried away there. That's lithium atom's electron configuration. If we look at lithium ion, remember it's lost that valence electron, so the ion should be smaller. Okay, so they are smaller. The cations are smaller than the original atom. This is what metals do. Okay, so let's look at anions. This is where nonmetals are gaining electrons. Notice it's the opposite. These are larger than their parent atoms. And notice what the reason is. It's due to electron-electron repulsions. Okay? And you can write the electron configuration of chlorine if you would like. It should end. I could do the shortened one, which would be neon in brackets, and it would be 3s2, 3p5. So I'm going to write that. Those are its valence electrons. And when it gains that one electron, we can see 1 because it's -1. It's 3s2, 3p6. So you can't just say chloride is larger because it has 1 extra electron. It's really not about that. It's because that 1 extra electron experiences more electron-electron repulsions and the cloud expands. Okay, so don't just say 1 electron makes it bigger. You have to go deeper than that. Okay, then we're going to get to number 3, and here's the definition of ionization energy. We kind of saw this and talked about it briefly with PES. This is the energy required to remove an electron from an atom in its gaseous state. Notice it's endothermic. Okay, we'll talk about that later, but that means it has to add energy, it has to take in energy, and we'll get into a lot of details with endothermic as we get to Unit 6. Okay, so for ionization energy, notice, and this sometimes is an easy way to remember, it is the opposite of atomic size or atomic radius trend. Because remember, the size trend, as we go across, the size is getting smaller. So what is the ionization energy doing? It's increasing. Okay, it takes more energy to remove an electron from a smaller atom. And as notice, I don't really like going up and down. I just always go down the group. So notice the ionization energy decreases as we go down the group. And why is that? Well, the size of the atom is getting larger. So it's going to take less energy to remove an electron from a larger atom. So these are the things we're going to work on explaining in just a moment. Now, when we're talking about ionization energy, and even we really talked about this with PES. These ionization energies could be numbered, as you see here. And a lot of times they'll be IE1, IE2, but this textbook just said use I's. But notice what the number refers to which electron you're removing. So IE1 would be, for sodium, it says it's 495. So that's the energy. Notice it's in kilojoules per mole generally. That's the energy to remove the first electron from sodium. Okay? If I need to remove a second electron from sodium, wow, it jumped up to 4,560 kilojoules per mole. So let's look at why is these stairs, why is this highlighted like this? So let's just kind of think about this. All right, so sodium, it didn't take much energy to remove the first electron from a sodium atom, but when you try to remove a second one, it greatly increased. All right, so then let's look at magnesium. Magnesium, it took a little bit more energy to remove the first electron, a little bit more to remove the second one, and then we see this huge jump at the third, removing a third electron. Aluminum, you see the trend, it takes some energy to remove it, takes more, a little bit more, then we see the huge jump. So why are these huge jumps at different places? Well, it depends on, and maybe you've already figured this out, think about valence electrons. Sodium has a valence electron, because notice sodium's a group 1 metal, its valence electron is 3s1. So that 495 is how much energy it takes to remove sodium's 1 valence electron. So why is it taking so much energy to remove a second electron from sodium? Well, think about where that electron's coming from, and one term for that is a core electron. That second electron for the sodium would come from the 2p orbital, which is a whole energy level closer to the nucleus and much more attracted. So you can see why it's taking that huge amount of energy. If we think of magnesium, its big jump was between the second and third. Why? Well, think magnesium has 2 valence electrons. It's going to take some energy to remove the first valence, a little bit more to remove the second valence electron. Once you get to that third one, it's no longer a valence. You're down into that second energy level. Think of aluminum. Aluminum is in group 13, 3s2, 3p1. So we've got energy to remove 1 valence electron, which would be the p electron, to remove an s, the second s, then we see the huge jump. So I think you can tell here, and this is really what you need to make sure you can see, is to analyze this data and look for the huge jump, because it won't be highlighted like this is with the stairs. So if I look at silicon, even without looking at periodic table, I should say, okay, valence, 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 huge jump, no more valence. Okay, so that tells me silicon has 4 valence electrons. Phosphorus is going up, it's going up, it's going up, it's going up, but notice none of these are like even doubling as we go even from 2,905 to 4,950. They're just increasing. It's this like 4-fold increase that tells us that phosphorus had 5 energy numbers, and then the 6th one, it was no longer valence. If I get to sulfur, 1, 2, 3, 4, 5, 6 valence electrons. You can see chlorine, and it's like off the chart. Okay, and we know chlorine has 7, and then argon has 8. So make sure you understand this trend and these large jumps in ionization energy. All right, the next periodic trend doesn't usually come up very much, but it's really the opposite of ionization energy. Remember, ionization energy is the energy we have to add to remove an electron. Electron affinity is the change in energy that occurs when an electron is added. So we're not taking away electrons, we're actually adding them. And notice these trends are not very perfect. I would say that for nonmetals, electron affinities are exothermic. So for nonmetals, gaining electrons that's what they want to do. They want to gain electrons so they can fill up their p orbitals. Exothermic means it would give off energy, which is the opposite of what ionization energy is. And then electronegativity, we'll talk about this briefly. This really gets more into bonding, because if you look at the definition, it's the measure of the relative ability of an atom to attract electrons to itself in a covalent bond with another atom. And so Unit 2 is about bonding, so that'll definitely come up again. Really, all you need to know, you can come up with a trend here. You just need to know that fluorine is the most electronegative element. Don't need to know the values on tables. If they needed you to know values, they'd give them to you. Really, what you need to know are the three most electronegative elements. It's fluorine, and then right to the left of it, oxygen's number 2, nitrogen is number 3. So that's kind of the trend. It's going to increase towards fluorine and decrease away from it. And because of these trends, we can really talk about reactivity of metals and nonmetals, okay? And really, this kind of goes back to what I was saying when we were talking about electron configurations, is that the elements in the same group have the same number of valence electrons. That's why they have the same properties. And for metals, notice the reactivity of metals increases going down a group. All right? And what we're going to see is it's because of ionization energy. The lower an ionization energy, the more reactive a metal. Okay? The less energy it takes for a metal to lose an electron, the more reactive it is. So notice group 1 are the most reactive metals, and francium and cesium at the bottom of group 1 are the most reactive metals. Okay? And it's the opposite with nonmetals. Okay? See, nonmetals don't want to lose electrons. Nonmetals want to gain electrons. And so fluorine is going to be the most reactive nonmetal. It does have the highest electronegativity. And so, again, just remember that same group, similar properties, same group, the similar properties are coming from the valence electrons. And really, when we talk about reactivity, for metals it's about ionization energy, and for nonmetals it's about electron affinity. Here's just some properties you might want to look over. We're going to talk about this term Zeph in just a moment, but this just kind of sums up properties of metals versus nonmetals. Okay, Coulombs law. We'll talk about this now in Unit 1 as we talk about periodic trends, and it will help you be able to explain and understand periodic trends, and it will also be used in Unit 2 with ionic bonding. One thing you need to know about this law is that it's a relationship we need to understand. It's not something you need to solve mathematically. You need to be able to speak about what the relationship in Coulombs law means. You can't just say this atom has a higher ionization energy than this one because of Coulombs law. You still have to be able to explain, well, what do you mean by that? So you have to understand Coulombs law. So in Coulombs law, notice all the definitions of the variables are at the bottom. F is the force of attraction between two charged particles. Q1 and Q2 are the actual charges of the particles, so like positive 1 and negative 1 if we had like NaCl. R is the distance between the particles, and distance has a greater effect on the force than does the charge because the term is squared. And then K is the constant. Okay, so Q1 and Q2, the charged particles. In bonding, we will talk about ions like Na plus and Cl minus, but in the context of what we're studying here is we're actually talking about the atom. So notice we have a positively charged nucleus, and we have electrons in different shells or energy levels that are around the nucleus, and the electrons are negative. So these are our charged particles. Q1, it could be the positive number of protons. Q2 would be, really it's usually about valence electrons, but we can use different things. So the greater the distance is between the positive nucleus and those valence electrons, the less attraction there's going to be. I tell my students, just think of like the analogy of two magnets. When they're close together, you can feel the force of attraction, but as you separate those two opposite poles magnets, you can feel the force of attraction dissipating. Again, we're not going to be solving this. Okay, so this is kind of what I just said. Opposite charges attract, same charges repel. Okay, so electrons are attracted to the positive nucleus, but electrons do repel each other. And that already came up once when we were talking about the atomic size and ionic size difference between like a neutral atom and an anion. And then the second point is the greater the numbers on the charges, the greater the force. So when there's a higher positive charge, like more protons in the nucleus, or in this case, a more positively charged ion, it would cause a greater attraction to chloride than, in this case, Na+. Or if we're talking about protons and electrons, there's a greater attraction the more protons there are. And again, as we said, the closer the particles are to each other, the greater the force. And you can see that. And there's a little video if you'd like to watch it. Alright, so when we're explaining periodic trends, I want to be very clear. You're going to see this term effective nuclear charge. And what I want to make sure you understand is you don't have to calculate it. And I'm just going to kind of draw a line here. Some teachers like to use this calculated value. With my students, we just talk about what the term means, nuclear charge, and really what this really describes. And this is the abbreviation for it. Z represents atomic number, so it's like basically it's about protons. So the more positive the nucleus, the more attractive force there is coming from the nucleus that draws electrons in or holds them in place. Okay? So stronger attractive forces require more energy to be overcome. All right, so this, talking about how strongly, how many protons are in the nucleus, using an actual number, we're going to get to examples in a minute, we're talking about these Q1 and Q2 charges. Okay. The other thing we talked about is that attractive forces are weaker the greater the distance between them. Okay, so distant electrons, and again we'd probably be talking about valence electrons, will be held or not as attracted as those electrons that are closer to the nucleus. And if you think about like in our PES discussions with those graphs, remember I said always look for the peak that has the highest energy number because that's 1s. Okay, why is 1s the most attracted? It's right outside the nucleus. The peak in PES that had the smallest value is going to be the first electron to be removed because it takes the least amount of energy to remove it, is the greatest distance from that positive attractive force coming from the nucleus. Now, shielding, I really don't use this term with my students. What it's really saying is that the electrons that are not valence, we call them core electrons, are basically blocking or shielding, is the term, the attractive force that's coming from the nucleus. So basically, everything that's closer to the nucleus is getting that attractive force more so than anything outside the core electrons, like valence electrons are not as attracted. Okay. This is really, if we talk about Coulombs' law, it kind of takes care of this. All right. So as you look at this bulleted point, shielding reduces the attractive force between valence electrons in the nucleus. making valence electrons easier to remove. In the AP questions lately, you tend to be asked to answer these kind of trends based on Coulombs law. So I would recommend make sure you understand how this affects Coulombs law. Distant valence electrons are not as attracted to the nucleus because of that distance. And shielding plays a part, but it's really not as important to mention. All right, electron-electron repulsion we already mentioned with the anions and the parent atoms. If we can minimize electron-electron repulsions, that puts the atom at a lower energy state and makes it more stable. Okay, so look at this last statement. More electrons in the same energy level or sublevel repel each other because of the increased charges. Okay, the force of the repulsion increases the more electrons are there, and that can make the cloud expand. Okay, so here are some examples. This is a good chart to fill out if you're asked to justify atomic radius. We need a period justification and a group justification. Remember, when you're using these period justifications, it's going to be very important to mention effective nuclear charge, which is protons, and when we're using a group trend, we need to talk about the location of the valence electrons in different energy levels. So this is more the distance argument when we're talking about a group trend. Okay, and then across a period, that is more of the Q1, Q2 charge. The charge. So if we look at this, notice these are just the definitions. Notice as we go across a period, so that's across, the size of that atom decreases. Why? Okay, so think about what's happening. Each new element has one more proton. Okay, so that's what it means. It's an increase in effective nuclear charge. The more protons, the greater attraction for the electrons in that energy level. So the size is getting smaller. If we go down a group, remember the size gets bigger. Every valence electron, the new valence electrons, as you go from one element to another in the same group, they're in a higher energy level, which has a greater distance from the nucleus, therefore are less attracted. So just make sure you kind of, in your own words, get a pretty succinct, you really should only have to explain one of these examples in maybe 2 or 3 sentences, no more than that. Okay, first ionization energy. Remember we said these are opposites of the atomic radius trend. So notice, why is first ionization energy increasing as we go across a group? Well, it's because that you have one more proton for every element as you go across, which causes a greater attraction for those electrons in the same energy level. Therefore, since the size is smaller, it takes more energy to pull an electron away or to remove an electron. And then as we go down a group, remember the size is getting bigger because the valence electrons are in higher energy levels. The greater the distance a valence electron is from the nucleus, the less energy it's going to take because the attraction is not very strong. Okay, and for the electron affinity and electronegativity, what we've said earlier is really enough for that. These are the two that are going to come up the most, in addition to our discussion between comparing the sizes of cations to their parent atom or anions to their parent atom. So those are the main questions you're going to see. And we included these multiple choice just practice questions that you could look through. So I'm not going to go through with each of these. It's a good way to test yourself The question is there, and then the answer and the explanation are on the next slide. And there are a couple free responses at the end that your teacher might want you to do as a group in class.